Okay, on to lesson 2. This is about gear ratios in compound machines. So we started to see a little bit of that gear train that was spaced out. Now we're actually going to be combining with other gear trains or even with other simple machines. So let's get started. All right, first off, if you want to go ahead and title this as gear ratios in compound machines, and make sure to number our page up here and to page number 1 of however many of this lesson we're going to have. Okay, so first thing, I want you to see this pattern that we have between gear ratios and compound machines. Please notice that these are very, very similar. We're seeing this out over in situation. Like thinking about this, you can really think about torque and force as being counterparts to each other in these formulas. And then also notice we can rearrange these formulas for output. And so what I want you to see, oh wait, is that what I'm doing? No, I'm sorry. This one down here was multiplying gear ratios together to get your total, same as what we did with our mechanical advantage. Did I mean to put that one there? Well, okay, that's okay. We'll do this part over here on our notes. I kind of screwed up on a slide. Sorry about that. Okay, so first, gear ratios are used similarly to mechanical advantage. So please note for yourself, mechanical advantage over 1, that's going to be equal to your resistance force over your effort force. And another way of saying that is to say your output force over your input force. And that, notice that that is the exact same pattern that we're using for gear ratio over 1. That's going to be equal to our torque output over our torque input, or our number of teeth out, number of teeth in, diameter out, diameter in. But remember the angular speed in over angular speed out, the one that looks like the butt. And then I do want you to rearrange these for your output force. So if I was going to rearrange this formula for output, what would I have to do to get output by itself? We'd have to multiply both sides by your input force, and then it would cancel out. And so that means that my input force, or my output force, F out, that's going to be equal to mechanical advantage times your input force. And it's the exact same thing when we're dealing with torque. If I was solving for output torque, I'd multiply both sides by torque in. It would cancel out on this side. And then I would have that my torque output is equal to GR, my gear ratio, times my torque input. And so that's just another way. If you know the gear ratio and your input of any of these things, then you can solve for that output really easily. Okay. So sorry, these were the wrong formulas to paste in there. Okay, so now our next example we're going to be doing is an example compound machine. And so you may need to take a moment to sketch this out. And here's my version of that sketch, way less pretty. What this one's trying to do, it's kind of confusing. The idea here, actually let me use the camera real quick. So the idea here is, what if we had a gear and some kind of a handle connected to it? I think I have one handle with me. So I have this handle, and we're kind of using this handle here as the wheel and then this diameter is my axle that is then turning another gear, and then that would have some kind of an output handle, so that would be connected to something else. So if we think of these things, I'm trying to put them under the camera. I need to put them in front of this camera. So I'm sorry I don't have an additional handle for you. I'm not doing just the best job. I guess if I could slide this one in here and slide this one here. Okay. We would need to have this be rotating like another bar or lever or something, but I didn't bring enough things home. But the idea here is that we're rotating. This is so hard to do. This is why we need two supports for our axles. And so if I can, I'm using the lever as a wheel, and then this is the axle, and then there's this gear train, and then we would have ideally another arm or another thing that would be like the second wheel on the other side. It's going to be driving that as the ultimate output. So that's hopefully makes a little bit more sense. I think what they're trying to do here is show you how you could make a handle using miscellaneous VEX parts, because this is just like a VEX rail and a shaft, I think, is all that they've got going on there. But that is what they're trying to deal with. The first time I saw that diagram, I was like head spinning, did not understand. But what will be helpful, I hope, is as we go through this one, I've broken it down. So here's the overall sketch, which I'm basically just drawing clouds for the gears to make it easier. And then this was me really trying to get those little like lever arms to look right. And then we're gonna tackle this as one piece at a time. So if we're just thinking about that first gear with this handle, we basically kind of want to think about the wheel as being the handle and the axle as being the gear, which I know seems very counterintuitive to be assigning these names like that, but that's technically how these things are functioning, because we are bringing that handle all the way around, and so it is acting like a wheel in this mathematically in the way that this is set up. Okay. We also know some things about this setup. I didn't bother actually labeling. I labeled the effort force and the resistance force, but I didn't label anything else on here because it's already as messy as possible. And as you can see, I messed up calling these two levers instead of calling them wheels and axles, and that's technically how they're being used. They're not being used as levers. Well, they're being used. They're similar. It's very similar. I think it's the difference between the fact that this is going all the way around as opposed to a lever kind of going back and forth. If that makes some sense to you, hopefully that helps. As long as we understand input versus output, we're really okay. All right, so in this sketch, I've got my gear. I tried a little harder on the gear. The gear has a radius of 1.5 inches, and so I want to make sure that we understand that that's this distance. This is a radius, not a diameter, that I've been given here. And also this handle length, that 4 inches, that's also a radius. That is not a diameter, because this is going to end up going all the way around and making a really big circle. But what's helpful is, because of the equation for diameter, 2 times r, and the equation for circumference, 2 times pi times r, or pi times diameter, all of that kind of cancels out. So if we're given radius instead of diameter, it's going to be the same ratio. Okay, so that would basically be 2 times the effort radius over 2 times the resistance radius. That's essentially what that formula would be for the mechanical advantage. Okay. So just focusing on this part for right now. All right, so we've got our effort diameter, which technically they are putting in radius here, not diameter, is going to be my 4 inches divided by 1.5 inches. Okay, and I'm not going to bother using the calculator. 2.67, well, here, let's do 4 divided by 1.5 and just see. So notice that this is a 6 repeating, so 2.67 is what we're going to be putting here. Okay, and since this is a mechanical advantage, no units. But this is the mechanical advantage for the first machine, for machine 1 in this compound machine. Okay, let's move on to the next machine. Okay, so next machine, this is just a gear train, and we have the 60-tooth radius that is our input. It is driving our output, which is the 24-tooth radius. Okay, so we know that apologies if you hear some doggies growling. They're just happy. Excuse me. The number of teeth for our output, that would be what? Well, this one down here is the output, so that's 24 teeth. That's going to be 24 over our input, 60 teeth. And that is 0.417 over 1. Draw my box kind of going off the page there. That works. Okay. Oh, they actually rounded it to 0.4. That's fine. Oh, last one. They already showed the work for you. Ah! Well, we'll just catch up then. So our last machine, that's our 24 tooth. 24T. And then that's connected to our 4-inch handle. And let me also note that the radius is equal to 0.6 inches for my gear. So basically, if I was thinking about this as a wheel and axle, my wheel is my handle, and that is R equals 4 inches, and then my gear equals my axle, and that is 0.6 inches. Okay, and let's go ahead and plug that in, write out our formula. Mechanical advantage is equal to dE over dr, which is going to be my 4, oops, yes, right. The technical, sorry, this is, I mean, it's the, this is my input here, excuse me, and my output, because the gears are doggies. David, sugar. Hi. Okay. I'll send you some dog playing videos to lighten up class. Okay, so I just about did that wrong. So that means that the effort is 0.6 inches and the resistance is 4 inches, and that is equal to 0.6 divided by 4. Well, that makes sense. 60 divided by 4 would be 15, so 0.6 divided by 4 would be 0.15. Okay, so now we have, oh, you have not, I didn't switch back over. There we go. There we go. Okay, so now we have for machine 3, 0.15 for our mechanical advantage. Machine 2 is the 0.41 or about 0.4, and then machine 1 was the 2.67. So if I want to get my total mechanical advantage, then MA total, that's going to be equal to MA1 times, well, this is weird. Why did they, oh, okay, they multiplied by those and then by that one. Okay, so MA1 times MA3, and that is equal to 2.67 times 0.15, which happens to be, here I do 0.15 times 2.67. It's about 0.4005, which you would round off to just 0.4. And then for our gear ratio, that was also about 0.4. We just had one gear ratio in this, and so then my gear ratio total, that's just going to be gear ratio 1, which is equal to 0.417. So I wanted to actually do this calculation to make sure that you know that they're not just, they're coincidentally the same, but that's not necessarily how that will always be. So that's my total mechanical advantage, and that is my total gear ratio here. Okay. We do have one more problem that we're going to try. Let's see, this was page 2 of however many. I'm going to go ahead and leave some space here and start on the next page, because I find that that will just be neater. Okay, so we're going to do compound gear train. And so let's look at this. It does a nice little animation putting things together. So my driving gear is this green one. I want you to make sure to see that the green one is your driving gear. I'm going to go ahead and draw a little, well, no, I'll wait till I put it all together, then I can draw it all at once. Okay, so we have our green gear is meshed with the yellow gear. That's what I want you to see for starters. So this is one gear train right here. Now, now these two are sharing an axle. And so that is not another gear train. We just have this gear sharing an axle. It's not meshed with anything, so it's not doing anything yet. So far, only these two are meshed. And the little white dots there are just to help you see that difference in rotational speed. And now we're going to add our red gear. And now see, the red gear and the blue gear are meshed together. So we have just in the middle, these two, the yellow and blue, they're the only ones where we have two gears on the same axle. The red gear is on its own axle, and the green gear is on its own axle. So let's go ahead and sketch this out. So I think I'm going to start with the blue. And then I'm going to put my yellow around it. This is actually kind of a lime green color because you're not going to be able to see yellow. So those are on the same. And then I have my green gear. I hope you can tell that that's a darker green. Is over here meshed with my yellow gear. And then finally my red gear, which is my biggest one, is meshed with